All right. Hi. Let me hide these panels. Perfect. So, well, thank you for having me. I'm Felipe Montealegre. I'm a postdoc in UC Berkeley. And sorry I couldn't make it over there, but hopefully this will be a good makeup for it. I'll be talking about a project that we have with my PI, Carl Bodiger, on environmental justice, like studying environmental justice, approaching environmental justice through the lens of open geospatial science. All right. So of course, geospatial data is a big thing in ecology. It comes up in many different like forms. We have both raster and vector data is very common. Landsat images from like satellites, biodiversity data, land use data. All of these are extremely useful for a variety of ecological purposes. And one thing, as many of you might know, the current standard for ecologists and for environmental scientists is to use licensed software, such as like products from Esri, like ArcGIS. And of course, this has some drawbacks. For example, it makes research exclusionary only, if your university has enough money for a license for Esri, which is pretty expensive. Can you actually use and reproduce the results that were produced with these tools? Which of course obfuscates reproducibility to a certain extent. It also makes the entire code sharing process less portable, since you have to be in a place where like you have the license active. For example, you have to be maybe on campus, or depending on how the license is managed by the university. But this introduces a lot of friction. And of course, like there's bugs that like closed source software like live longer than in open source software, which is of course a problem for reproducibility, for like having stable results over time. So like our project was trying to draw attention from the environmental science community to some of the open source tools that exist, and also try to see how far we can take it. Like how far can we take the open source cloud native approach to geospatial data in environmental justice, and see if we can like find any places where we are missing tools. So kind of like it's got two parts. And yes, so like basically it's mostly a project where we are not doing original research with, but we're more reproducing classic results and learning by example, and also teaching by example. It's a teaching type of project. And this is part of the NASA TOPS program, which is a program essentially around that idea of, like engaging scientific communities in open science, in how to make open science like a reality in different fields, in our case, in environmental science. All right, so this is the homepage of the project. So we have some tutorials in R and in Python. We have some description. I won't go into it. I can send the link in the over email later, or I can also just show you the the web page in a moment. All right, so there's right now we have like two tutorials that we've developed, and we're like developing a few more. Um, the first one we developed was on exploring the legacy of redlining in access to green space, and this is like a very well known phenomenon that I'll go into in next slide. And then we have a tutorial on how to access cloud native data from NASA data centers. So, all right. Um, I'll jump into the project to the tutorial on redlining to maybe give like a little bit of a overview of like what we're covering generally. So as many of you might know, in the era after the Great Depression, the Homeowners Loan Corporation started creating risk maps of cities around the US to try to incentivize um, investment in housing, which was of course done with a very hard racial prejudice. Like it was, like with a very with very stark racist ideals and realities behind. And these types of maps, these types of classification of areas of the cities in terms of like the risk for investors were actually legalized during the civil rights era. If I'm not an American, so I'm not like an expert in American history, but I think this is what happened. However, we know that historical realities don't end the moment you illegalize them. They have effects that like can be observed decades after the fact. For example, they have been, like associated with environmental disparity, environmental quality disparity, heat islands, islands of like, like higher pollution. Um, Yes. So there's a variety of consequences. It has even gotten to the point where we can see like ecological and evolutionary consequences, where like animal communities adapt to the cityscape in a way that reproduces the like the grading of the cities. So basically, like there's biodiversity distribution that like essentially follows patterns closely associated to these grades. So what we're trying to do is observe that using open geospatial data. Um, so I wanted to like take a screenshot of like, like the type of like tools that we use in the Python tutorial. So as you can see, we use both vector data, which is the polygons of the grades. We use raster data, which is from uh, satellite images. Sorry. um, and yes, we will be computing some zonal statistics on these polygons. So essentially, from the satellite images, we compute an NDVI, which is essentially a measure of greenness. And what we will be like the goal is to like show that access to green space is highly associated with the grade, the whole C grade, the red line grade. So here we have a map of San Francisco, and a map of the NDVI of San Francisco. You can see, for example, the Presidio Park, the Golden Gate Park, and so on. And we have a map of the polygons of the different yeah, like whole C grades neighborhoods. And we can see we already colored it with respect to like here what we're computing is in each polygon the average greenness or the average NDVI value, and then plotting that as the color of the map. And then of course we reproduce, like we get that essentially red-lined neighborhoods have a considerably lower value of NDVI in their polygons, which we can kind of like this points in the direction of having less access to green space, which is something that is like a association that is already pretty well known in environmental science. So that's good that we can reproduce that. We've run it for different cities, for Chicago, for LA, for San Diego, and it's always like a very similar phenomenon. There's some where it's like more pronounced, and LA is more pronounced than San Francisco. But yeah, in the end, it's pretty much the same phenomenon throughout the US. All right. So with that, like little, little droplet of like what the project looks like in a bit more detail. Let me kind of like start wrapping up. This is like a very short presentation. I'm sure because presentations in Zoom are sometimes a little bit like awkward. I'm sure it's good that it's short. But let's see. Let me. Oh no, sorry. I just wanna like put all the challenges in in the slide. So let me see. So like one challenge that we came across is processing large vector data files. So sometimes there's like a gigantic zip with vector data in it, somewhere in the cloud. And we couldn't find really good tools for subsetting the data in a cloud native way for just, like downloading the relevant parts of the data that we want, for efficiently getting metadata that is relevant for us. We started playing around with DocDB Spatial, which seems to be a great tool. The one problem is it's not super native for Python yet. There's no Python API. As with like regular DuckDB, you have like the IBIS framework. The DuckDB spatial, you have to like still do the thing where you know, like create a string with the actual like, you know, DuckDB CLI commands, and then put that into you know, like the correct method in IBIS, which isn't like bad, but of course it would be better to have, you know, like proper, you know, an API directly in Python with like documentation for the Python API. And then there's been some like hiccups on like computing statistics, or like zonal statistics, and yeah, just generally like, you know, like mixing vector data with raster data. We have been able to do this, and it's mostly okay. The one thing we found is that in Python specifically, the tool, you can see it, this let me, oh no, let's see, it's this tool, zonal stats from raster stats, that requires you to actually like save both files to disk, and then provide the, you know, like the paths to the files to be able to compute the zonal statistics, which is of course like, it's not too bad because we already subset the data by that point. We only are saving the relevant parts, but of course it would be better to not have to write to disk, and just compute the zonal statistics in objects. So that was one hiccup that we encountered. And then we had encountered some hiccups with accessing certain NASA datasets. For example, like the NASA CERAC doesn't communicate with the tokens of like the Python API that NASA provides, of Earth access. So of course that's also another, and like this is something that is like being worked on. Like they have a very active channel, the NASA tops, and they were like very happy to like, you know, like start helping us out. But of course, yeah, this is of course something to like work and continue working in the future. And okay, let me wrap up with some opportunities. So, okay, so like what we're very excited about is creating tools to democratize access to GIS analysis in a portable way. So you don't need like access to a huge compute center to be able to do things. Which we hope will reduce the price of research and make it accessible to more people with, you know, like in universities with less funding, which is of course very like a very important thing. I myself, I'm from Costa Rica, and I know I studied in the University of Costa Rica, which is not particularly known for having a large budget for research. So that would be amazing. Um, let's see. We also want to like facilitate data processing under data sovereignty. And this is of course a very, very long topic with a lot of nuance, but like essentially the idea is to produce methods that can be helpful, like that are portable and reproducible, that can be helpful for example, like tribal environmental managers, which might not have like access to like large compute resources, and which can actually like take this, you know, open source code and repurpose it for their you know, like for their own objectives, and not have to like share any of the details under that license. So yeah, and this is the second point I was making, this MIT license tools that can be useful in this respect also. And then I know that there's you know, like some activity in the decentralized web right now, and in this conference, and I'm not like an expert in the decentralized web by any means, but like I was like reading about it, and I was like thinking about it, and I think one thing that would be cool for this, an opportunity that would be cool, I'm not sure how realistic it is, but it would be having data that is already subsetted in a decentralized way, with, you know, like with the correct infrastructure, with the correct metadata, with the correct, you know, like standards. It might make accessing you know, data in a cloud native way more natural, because it could mean that, for example, you might only need the data that is stored in a small node. instead of like accessing this like big node with all the data at the same time. Of course, as an environmental scientist, also like another thing that comes to mind is, well, but like what is the, like the price in watt per like service unit, for example, versus one that is in just like one single big node. So yeah, I don't know. That's the things I've been thinking about. I think it's a very interesting topic with a lot of opportunities. And yes, yeah, and yeah, like last is, like it could help enforce some data native formats, like small chunks, efficient communication and so on. So anyhow, thank you for your attention. I almost filled up my 15 minutes, so sorry about that.